Our speaker today is Mark Bourassa, who is going to talk about coupled air-sea interaction and some modeling results.
Thank you, Sarah. So this is a talk I'll present with work from Jackie May's PhD work at Florida State University. Jackie works for NRL Stennis and really did almost all the work I'll talk about, but I'm refocusing it for the winds and currents related activities for WACM, whereas she's done something much broader. We're interested in whether the feedbacks between the ocean and the atmosphere are important. Traditionally, a meteorologist tends to assume that the atmosphere will not meaningfully modify the ocean on small spatial scales, while oceanographers do the opposite, where they assume the ocean won't modify the atmosphere very much. On large space-time scales, this is, can be done with thermodynamic feedbacks, and we ignore winds and currents. However, fairly recent work by Leon Renaud and colleagues, and she and this other guy have found that this coupling is important. It tends to dramatically reduce the eddy kinetic energy flux, so that reduces the eddies in the oceans. It tends to make the currents more zonal. There's changes to the currents, to the energy transport, to the boundary layers in the atmosphere and the ocean. So it does have an impact. But when we model it, I'm going to show that it changes the ocean and the atmosphere, obviously, but is there a feedback that's important? Can we just model these processes by making in the atmosphere by using winds that are surface relative, or in the ocean by calculating our stresses from surface relative winds? If there's no feedback, that's okay. I'm probably going to tell you there's a feedback. Let's check. These are images of the curl of the stress. And this is from Jackie's work. We're using the Navy's coupled model system on a 2-kilometer grid. And the image you see now is based on the model that's only coupled thermodynamically. So winds are Earth relative. And you can't see any sign of the currents there, which is to be expected from a curl of the stress. Now, if we calculate this curl in with currents, winds that are surface relative, where we take the current into account, we see a huge change. And if this is the only change we get, then we don't need to measure currents. We can work simply by measuring Earth relative winds. But when we look at the same fields from the coupled model, where we can have feedbacks, we see that there's quite a large change. So feedbacks are important. That's a fairly straightforward conclusion from high resolution coupled model of winds and currents. Feedbacks are important, and we don't understand how strong they are. So that's something I'm going to talk about and explain the process. So this is a conceptual diagram of what's going on when you have, in this case, an example with the Gulf Stream extension, where we have the currents coming toward us. The south is to the left, north is to the right, and the winds are blowing parallel to the current. And again, it's always going to be a surface relative wind that's going to count here. We can get a divergence in the water on one, or a curl of one side on the water, vorticity of the other side on the other. And above it, we get the opposite pattern in the winds. And that induces a curl in the stress as well. So we see these in Doppler scout observations. It's something Alex Weintier and Ernesto Rodriguez have shown a lot. We know it happens. But because of this curl, we also get Ekman motion in the ocean, and we get a secondary circulation in the atmosphere as well. These secondary circulations are in a vertical plane as well as the horizontal. So we're going to get the Ekman upwelling and downwelling in certain places and the corresponding currents at the surface. And in the atmosphere, we're going to get convergence and divergence with the associated upward motion as well. So this kind of pattern is what we would expect to see if this is if this current and wind coupling happens. And let's see if we see parts of this in the model. But before I get there, for those who haven't done a lot of this kind of modeling, why does the shear strain change? Why does the wind stress change due to the current or due to other things? And the simple explanation is if winds and currents are in the same direction, then the shear between the two is reduced. And this is a model for shear stress. Then if the currents and the winds are in the opposite direction, the shear increases and the stress increases. And that's what we're seeing mainly with the currents. But other things are happening. We get changes if this is all assuming the winds aloft are staying roughly the same in the simple model. If we get changes in stability because the air sea temperature differences have changed, and they do change, then having it more stable will have less stress, and more unstable will give us more stress. And similarly, if waves are important, having steeper waves will increase the stress and less steep waves will decrease it. So swell tends to be high, but not very steep, and it doesn't have much stress, whereas wind waves are where most of the stress comes from. In this model, we don't have the waves connected. In prior work, we have worked with waves, and we find that they do amplify, at least with the parameterizations used in that model, they amplify this coupling. So the feedback we get in here, that again, this model is having the winds parallel the currents, and we get a Ekman motion from the right of the winds towards the current, and that compresses the current, compresses the current gradient at that point, and because our stress curl is a function of distance, we get a same change in stress over a smaller distance, we get increased curl, and it's a positive feedback. On the left side, you get a small negative feedback. And this is some of the feedback that we think we're seeing when the model is producing that huge change I showed you. So do we see more compressed currents? This is an example that is opposite the one I've been showing earlier. We now have the winds going against the currents. So I'm going to flip the diagram over. You can't read the words, but the arrows are all lined up correctly. And we get the enhanced current gradient on this side, or the enhanced SST gradient as well. So in this example, on the left, we have an Earth relative coordinate where the current and wind coupling hasn't taken place, and on the right we have it with the coupling. You can see we have a stronger sea surface temperature, or surface temperature gradient, or temperature at any depth gradient here, and it is what we expect from that kind of coupling, which is nice to see. So again, this is the coupling we're looking at over here. One of the other results that was interesting was that the depth of the thermocline was much more stable in the modeling when we had that kind of coupling. What about the vertical motion? In this case, it's the same example. We have a very strong system, and we have some pretty strong vertical motion up over here, and this is not really the motion, we're transporting heat down. And this was presumably cold water sinking from massive fluxes under a storm. And we suppress that when this coupling has taken place. So it looks like we're having this secondary circulation in the ocean. We also have it in the atmosphere. But in the atmosphere, one of the questions we have is how do the winds align on the surface with respect to the current? And in the uncoupled model, of course, they don't, because it's not feeling the current. It aligns mostly with a stress gradient in terms of advection of momentum. But in the coupled model, it does align very strongly in the cross current direction, like we'd expect. So that's again reassuring that we're seeing this secondary circulation in the model, and this conceptual model seems to be fairly effective. Now, to get this, I want to emphasize that we do need to run at high resolution. If you run at 25-kilometer grid spacing, you're not going to see this, or not much of it at least. So one of the questions we still have in trying to understand this is how fast do these adjustments happen? If the time scale is very fast, then it would come into balance quickly and it would be really probably easy to model. If it's really slow, then it doesn't matter as much because it doesn't happen. You just see very slow changes. It's probably somewhere in the middle. Um, the feedback scale is presumably related to Ekman processes. So you say roughly an inertial oscillation scale. And that's a non-negligible time scale unless you're at very high latitudes. So while this is fast compared to thermodynamics, and it does allow the atmosphere and the ocean to adjust much quicker than it would just with thermodynamic feedback, it's not fast enough for a system to come into equilibrium with a passing storm, unless that storm is very stationary. So when we're looking at these relationships from model data, we can't assume they're in equilibrium, which does make it harder to look at these processes. And also, since stress rather than wind speed is a key factor in this simple model, and stress is a nonlinear function of wind speed, we expect to have a much greater impact for higher winds than we do for lower winds. We see that. We see it in the Navy's model, and we see it from just estimates based on a bulk parameterization that the impacts are much greater at higher wind speeds. So here's some atmospheric examples. This is an extreme case that I found fascinating. We have an atmospheric front passing over an oceanographic front. So it's frontal interaction in both ways. In the uncoupled model or dynamically uncoupled model, we have this increased atmospheric convergence and divergence associated with the front trailing off to the north, which is what we expect, and this enhanced convergence and divergence, which leads to vertical motion over here. But in the coupled model, where the winds and the currents are coupled, it's dramatically stronger. So this is going to be very important for mixing geophysical properties or materials from the boundary layer up into the free atmosphere. In this case, you're pumping it up to the top of the free atmosphere. So one of the applications I was talking with somebody about yesterday is lofting of salt into the atmosphere. This kind of process could be very important for getting oceanic salt higher up in the atmosphere where it affects chemistry. If we look at the vertical accelerations associated with these two different areas in the boundary layer, same box in both models, we can see that there's much stronger vertical acceleration in the two-way coupled model. So this coupling is having a fairly decent impact, admittedly only where you have strong current gradients, in both atmospheric and oceanographic models. So when we're trying to characterize this, there's two key processes: a curl of the wind and a curl of the stress. And actually, it's supposed to be the wind gradient in the crosswind direction, or the current gradient in the crosswind direction. That's right. And I've put them both on these plots. So in our conceptual diagram, those are the two key characteristics for feedbacks. And in the uncoupled model, or the undynamically coupled model, we see almost no sign of this feedback. But when we look at it with just calculations in an Earth relative system, but uncoupled, we now see a substantial feedback. So you ask, what's different in terms sorry, this is a non-feedback system here. What's different when we add feedbacks? Because if it's small, then we don't need to worry about it. And it's not immediately clear what happens. It's very clear that you get some change in the processes pushing things in this direction. It's much more organized around current gradients than it used to be in the uncoupled model. So they're playing quite a role, but it's not immediately clear what that role is. So they're clearly having a big impact. Feedbacks are important. But when we look back to prior work that she and I did back and published in 2019, we had this kind of relationship here. So it's a fairly nice cluster. And this is based on a month of averaging, whereas this is based on a much smaller time period. But we get a different slope. And this green line represents that slope here. We can see hints of it in the Navy model, but these are very different. And there's reasons a lot of reasons they could be different. The model on the left included the sea state impacts on stress, and they did so in a model that was fairly exaggerated, probably, but not awful. So it suggests that the sea state could be playing an important role in this coupling. The right model is with coamps, and it had a lot of the mixing turned off. So that may have changed things as well. And it's not clear. This is something that's going to take a lot of work to understand. So can we do something with this if we had a satellite that measured winds and currents? Well, the key processes involved here are stresses, and scatterometers measure a wind that is really a stress, but it's made to look like a wind for various reasons. So that's good. And we need current gradients. So if we measure currents, we can get current gradients. So we can ask questions like, how much does the curl depend on the wind speed aligned with the currents? And again, in a current relative sense. How does the current gradient to the right differ from the current gradient to the left? Again, of the winds relative to the current. Because if there's this feedback process, we expect them to be different. If there's, and the duration or the time it takes for this feedback to happen will be an important part in addressing that as well. Do these gradients really depend on the magnitude of the wind speed? Probably. It sure looks like they should. So are these answers different in the tropics? These two studies I've looked at have been mid-latitude Gulf Stream extension regions. And there's the physics should still apply in the tropics, but the wind speeds are lower. On the other hand, they're more persistent. So they may still show up as a reasonably strong signal over short distances. Over long distances, the stuff Dudley has done with SSTs will be a bigger player. So for Wacom, are these practical questions to ask? We would need to retrieve winds and currents. We can do that. We would need them more for moderate and high wind speeds than for low wind speeds. We can do that. Storm cases we can't see them with Wacom because there will be, or in most cases we can't because there's too much rain in the way. And that's okay to drop out because they're probably not going to be in equilibrium or anywhere close to it. So it'll be harder to work with. So that's not a bad thing either. And if we're looking at storm systems, behind them, we tend to have an atmospheric colder air mass, which is rain-free and high winds. So looking at higher latitude environments, we'll certainly get cases where we can test that. And I'm really interested to see how much this would be important in the tropics as well. So in conclusion, it's really important to have winds be surface relative, particularly when you're modeling at high resolution. The feedbacks are important. It's not just a matter of going to this better coordinate system where we make things surface relative. The feedbacks are really important. The secondary circulation we get from those changes the structure of the ocean, the magnitude of the currents, the structure of the boundary layer of the atmosphere a little. It's not a lot, otherwise we'd have seen it before, but it does noticeably do it on a long-term mean. The impacts are greater when the stress is stronger aligned with the current. The component of the stress along with the current has to be strong to see, well, it doesn't be strong, but stronger it is, the easier it is, you'll see it. Models don't agree, so it's hard to use a model and just say this is the answer. And an instrument like Wacom could quite reasonably help us understand this coupling, which seems to be very important for weather and climate. The changes and fluxes we're getting are enough to impact climate, they're enough to impact weather. There's a lot of things we could look at down roads, processes that would be really interesting with this. All right, thank you very much. I'm happy to take questions.
Thanks, Mark. This was great. questions from anyone?
I should thank ONR for and no one NASA for paying for this work.
Well, while people are thinking about questions, I'll ask my question. You showed results from a 2-kilometer ocean and 2-kilometer atmosphere, and a potential satellite instrument might give us 5 and 10-kilometer resolution. What will that do?
Well, it'll capture most of this. The 2-kilometer ocean is more like a 4-kilometer satellite resolution. So it, or 4 times the grid spacing. So it's very similar. So I think we will capture most of these processes with that. It's something we do need to double check before we brazenly claim it, but it certainly for 5 kilometers more than adequate, and the 10 kilometers probably adequate. You can also look at the first images I showed and see the scale of the impacts, and it certainly exceeded those scales in the spatial scales with that first image showing the feedbacks. So
do you have a sense of what the transition scale is between this process being dominant and more thermodynamic processes being dominant?
We're still working on that, but Larry O'Neill, Dudley Chelton, and others have shown that on long scales, the thermodynamics is clearly relevant. And we know that the importance of this drops off as the distance gets larger, because you have the same change in current. You don't get a bigger change in current as points get further apart, which you can get bigger changes in SST. So if we're calculating a curl, then with that change, it has very, very little impact. So Larry has shown with buoys, and Dudley and others have shown with satellites, that the currents or the SSTs are important at 25 kilometers, but not sufficient to explain things. It's not a stability related process. It's too small a scale for a Lindsay-Negum type process. So somewhere in that 25-ish range, we're getting a change, but I don't know exactly where it would be.
Well, hopefully an open question for future work. There's a question in the chat from Megan Cronin. Megan, are you able to unmute and just ask?
Okay, sure. Thanks, Mark. That was great. That was really interesting. So you, in your bullet point, actually, could you go back to your summary there? You were saying that these impacts are greater when the wind stress component is aligned with the current is stronger. I can understand that this feedback would have a bigger impact when the winds are aligned with the front and the currents, but is it true that the impact would be larger when the winds are larger? I would have thought that the impact would be larger for weaker winds, where the currents are more of the same size as the winds. So could you just kind of clarify about the sensitivity to the wind speed?
That's a really good question. So that's the assumption most of us started with, and we certainly went from there. But what we're looking at is a change in stress, and the impact of a difference in speed in this calculation of stress is much larger when you're at higher wind speeds. So a difference of 2 meters per second at low wind speeds causes a much smaller difference in stress than at high wind speeds. So I checked on that just to show the impact. And on this axis, we have the change in stress and the wind speeds on the bottom axis. And you can see the change in stress for a 2 meter per second change here, 1.5, 1.5, and then so on for the opposite direction. And as the wind speed goes up, it's a nonlinear response, and you get a bigger impact. Now, again, in the tropics, though, the winds are much more persistent than they are at higher latitudes. So they have more time to integrate and have the impact seeing. So I'm not claiming that it's negligible in the tropics with lower winds from this. I'm just saying you'll get a more immediate, stronger response.
That's really surprising. Interesting. Thanks.
You're welcome.
There's now a question in the chat from Jinbo Wang. Jinbo, do you want to just go ahead and ask?
Yeah, thanks, Sarah. Thanks, Mark. Yeah, my question basically is just how to take this and think about the mission requirement, the resolution, and the noise level.
So the resolution, I think we could probably work with 10-kilometer resolution and address this, which we can achieve. We can do better than that for winds. The noise, I've carefully picked objectives when I suggested these topics where a large number of observations could be combined to reduce the impact of the noise. It's just an averaging issue, assuming the model function and whatnot handles everything else to remove any trends. And even this, we're taking mostly differences. So even a poor calibration is going to be relatively insensitive to that. So for these questions, the noise is not as important. If we start trying to look at this relationship, the noise does become more important, but we still could calculate this kind of slope. It's just, it would take a lot more observations to do it. So
yes,
it is doable. And it actually plays to the, it doesn't have trouble with the weaknesses WACM might have at low wind speeds. We can't maybe get currents at really low wind speeds. We can't see through rain, that kind of thing.
I see, thanks.
Dudley, do you want to go ahead and ask your question?
Yeah, hi, Mark. Thanks for that nice presentation. You just said that you thought that 10-kilometer resolution would be adequate from WACM. And I'm just wondering whether when you say that you have in mind the wind stress components or the wind speed components or whatever, or do you have in mind the derivative fields like the curl or the divergence of the wind?
Yeah, that's an absolutely critical question. I should have been more precise in my answer. Thanks, Dudley. I'm thinking point resolution when I gave those numbers. So it is doable.
Great. Lionel, Renaud, do you want to go ahead?
Yes. Hi, Mark. Thanks for your talk. In previous studies, based on coupled simulations and observations, we estimated coupling coefficients between surface current vorticity and surface stress curl, and wind curl and current vorticity. Did you try to estimate these coefficients in your simulations?
We did not. They are very well matched, but we did not try to estimate it. We did find we had similar reductions in eddy kinetic energy and the like that you found. So I doubt if the answers are very much different, but we can look into that.
Because actually we also found that the coupling coefficients, basically you can interpret it as efficiency of the current feedback of the eddy killing, and the larger the wind is, the more efficient is the eddy killing. So the stronger response you will have, both in stress and in wind.
So, okay. Oh no, thank you. That's an excellent suggestion. So we'll definitely look into that.
Other questions? Oh, I see Jacob Wintergard has raised his hand. Go ahead.
Hi, Mark. Thanks for the talk. I guess my question is whether you have a sense of the sort of small end cutoff of where this matters, right? So you showed that the kind of Ekman dynamics here lead to frontal sharpening, but then we know when we get down to, kind of true submesoscales that other ageostrophic dynamics probably take over. So do you have a sense of, where that transition might be, the kind of current feedback effect on Ekman towards other frontogenesis mechanisms and how that might show up, in sort of Wacom type observations?
Oh, great question. So one of our postdocs, Xu Shen, has looked into that with a sub-mesoscale model where he had roughly 100-meter grid spacing. And he found that the importance of the process continued down to that scale, and it actually becomes more and more important. Although we did find that SST gradients, like Dudley has looked into, never disappear in importance. It's just the winds dominate on smaller scales. So I don't know how far down it goes beyond that, but it's certainly well into sub-mesoscale.
Thanks.
Although actually, Xu's model didn't have feedback, so I can't address how far the feedbacks go back down.
If I can ask another question, I was wondering what you thought the role of surface waves might be in these processes. Is that something that's built into the model you're using? And if it were, what would that do?
I'll start with the other order. We turned it off for this model. So we just used winds and ocean. In the prior work, we did use a wave dependency, and we used a Taylor and Yelland stress. The stress model was dependent on those waves as per Taylor and Yelland's model, which is a pretty good fit to data, even if there are aspects of what we know are wrong in terms of winds and currents going in the opposite direction. And when we used that wave model, the waves were clearly non-negligible. They had about a 30 to 50% increase in this coupling that we saw in the Xi and Bourassa study. So I think they are important, but keep in mind that how the stress depends on wave characteristics is incredibly controversial. For each scientist working on that topic, there's probably two ideas of how important it is. It's not clear at all. And we may have considerably overestimated it with that model. In fact, I suspect we did.
Yeah, your hand up.
Hi, Mark. Just following up on that, for that case, did you have the waves both feed back into the atmosphere and to the ocean as well?
We did. So in that study, let me see. This is the monthly average change in stress we got in the work with the waves included, so waves and currents, relative to the model without the dependency on waves and currents. And this would be the curl of the stress, or the Ekman, let me see, what is it? Well, it's the pattern for the curl of the stress. So it's bigger, and adding the waves helped get a more uniform pattern along the currents. So it did seem to help with the organization.
Sorry, I guess my question was if you had waves and ocean coupled. So did you have Langmuir turbulence in the ocean model as well at the same time?
Probably not. I'd have to remember back on that work. I don't think that particular parameterization included Langmuir or Stokes drift directly in it. It may have indirectly parameterized it in there.
Thanks.
And those are things that the ocean modeling community is still trying to get better at.
Yu Gao has raised her hand and put a comment in the chat.
Yes. Thank you, Mark. So I wonder if you have any findings in terms of how the wind, in terms of how this wind current interaction affect the thermocline structure or the mixed layer depth.
Yes.
At the submesoscale, since you mentioned it briefly.
Well, I can show you examples from what we did. Jackie's work actually included a lot of that. Let me see if I saved any of the examples. So these are examples of this similar section I showed before, but this is for a 2 kilometer section this is for the ocean and the atmosphere both being 2 kilometers, the ocean and the atmosphere both being 6. And you can see the sea surface temperatures here across the model. And this is for no feedback. And then when we added the feedback, it stabilized things. It did push them over a bit, as we said they would with the feedback process. It also stabilized the depth of the thermocline line a lot. So there are some pretty substantial feedbacks there. Did I answer your whole question?
Yes. So basically, with this feedback, the mixed layer is more stable. The
mixed layer is more stable. The current trajectories are more stable. Even when we do things that we shouldn't do, where we mix resolutions, it tends to stabilize the current trajectories.
Okay, thank you.
You're welcome.
Can you explain, Mark, quickly? Do you mean stabilize in time or in space?
Oh, good question. So it's more zonal, both in time and space.
Okay.
Although we only looked at 2 months, so take it more as a spatial confirmation. But Lionel's work earlier showed that it tends to reduce the eddies. He showed the same thing.
Oh, a side question. So when you look at in terms of it's shallower or deeper, does it tend to get shallower or deeper, or just tend to get less noisier?
Less noisier, definitely. I don't remember the shallower or deeper part of it.
Okay, got it. Thank you.
Jackie's online. She might be able to answer you.
Lionel.
Yeah, just to complete that about the Gulf Stream, actually with the current feedback, you stabilize the Gulf Stream path and the separation of the Gulf Stream so that you have a much more stable Gulf Stream. And then to me, the modification of the mixture depth is more a rectified effect than a direct effect.
Yeah, that's fair.
Okay.
Thank you.
Thanks. Bia, you got your hand up.
Hi again. Mark, you did comment a lot on like spatial resolution. I wonder if you could comment on temporal resolution. Like work led by Donati Agliglio has emphasized the importance of wind gusts and sort of like how we're thinking about that, both in terms of this model and Wacom in general.
That's a really great question, which we haven't dug into, but conceptually, if you have a wind gust, it will give us this burst of action. And if the positive feedbacks are strong enough on that side, you'll get a quick response. On the left side of the winds, you'll get a slow response. And it could gust back and forth and end up having the stronger positive feedback impact dominate on both sides of the current, for example. So this is something that's probably not critical for a Wacom study, but it would be really, really fascinating to look at. And I haven't looked at Wacom sampling in time and this variability to see if we could address it. But scientifically, it's something I'm very interested in.
Thank you.
Yeah, I think it's a great question. Any other questions? This has been a great discussion. And I think we probably could keep going with a lot of open questions for a while, but maybe we'll wrap up here and leave further discussion for the next time. Thanks, Mark, and thanks everyone for participating.
Thank you. Thanks for the great questions.
Thanks, Mark. Thanks, everybody.
Thank you, Mark.
Thank you, Mark. Great talk.
Thank you. I shouldn't be getting that nervous talking. I'm clearly out of practice. Anyways, thank you.
It was
again,
great.
Sarah.
Thanks, Mark. It was really good. I thought that stimulated a lot of discussion and opened a lot of questions. And I think you explained what you were showing really nicely.
Thanks. We've been struggling on that. And then, this is mostly Jackie's work. So she really deserves a huge amount of credit on this. But she's with Greg. So if we work with her, we've got it. All right. Anyways,
Yeah.
thank you very much
Great.
for facilitating that.
Yeah. Thanks. Wow.